What does this problem say? It says that if lambda is an eigenvalue of A, then it must be an eigenvalue of A transpose. Well, let's take lambda to be an eigenvalue of A. What we then know is that A minus lambda I is singular. That was one of the ways in which we could identify eigenvalues. And what that means is that the dimension of the null space of A minus lambda I is equal to K, some number greater than 0. But what do we know? We know that if A is a square matrix, then the dimension of the null space of the transpose of a matrix is the same as the dimension of the null space of the matrix. So we get this. And then we can just work out what this transposed is. And what we find out that now we have that the dimension of the null space of A transpose minus lambda I is some integer greater than 0. And that means that there are eigenvectors to be had. In other words, A transpose minus lambda I is singular. And thus lambda must be an eigenvalue of A transpose. So that one is kind of tricky because you really have to understand about null spaces, you have to understand about how eigenvalues relate to matrices being singular, and you have to understand how the dimensions of the different the four fundamental subspaces are related. So this one brings together a lot of material that we saw before. Once you prove that, this one should be easy. So you can pause the video or we can keep going, whatever suits you. So obviously, if lambda is an eigenvalue of A, then it's an eigenvalue of A transpose. We just proved that. But notice that A is A transpose transpose, so therefore it also goes the other way. So let's go back to why 1 is an eigenvalue of P, the transition matrix. It's because of the following. If you look at P transposed rather than P, notice that if you multiply P transpose times a vector that's all ones, what do you end up doing? Well, this first entry ends up being this column in a product with 1, 1, 1, which just adds all of those entries, but the columns of a transition matrix must add up to 1, and so forth. And therefore 1 must be an eigenvalue of P transpose. But if it's an eigenvalue of P transpose, then it's an eigenvalue of P. So now we know that if P is a transition matrix, then it must have 1 as one of its eigenvalues. So let's have a look and see if we can visualize the eigenvectors and eigenvalues of a transition matrix. Now notice that we have a tough time visualizing a 3 by 3 transition matrix. So here I picked a 2 by 2 matrix, and notice that it's important that the entries in each column add up to 1. Again, we're going to sweep X around the unit circle, and we're going to observe what happens to A times X. And let's have a look. First of all, notice that it seems like one of the eigenvalues is roughly 1/2. Actually, if you calculate it, it's exactly 1/2. If we then go on, when we end up pointing in the direction of x1, we notice that vectors x and A times x are exactly the same length. So the eigenvalue is equal to 1, which is what we expected. It disappears again. Clearly one of the eigenvalues is 1 and the other eigenvalue is smaller than 1. That's actually the important part. Why is it the case that eventually that vector doesn't change anymore? Well, we can analyze that using eigenvectors and eigenvalues. We know that the eigenvalues of this matrix include 1, and for the particular transition matrix that we have here, we actually know that lambda 1 and lambda 2 are less than 1 in magnitude. As a matter of fact, they're between 0 and 1. Let's look at the three eigenpairs for this matrix, which gives us then three vectors v0, v1, and v2, and I'm using v because we're already using x for something else. Let's assume that these vectors are linearly independent. We haven't proven that, but let's just assume it. We know that if they are linearly independent, that the vector x0 can be written as a linear combination of those three vectors. So the coefficients then are gamma 0, gamma 1, and gamma 2. If we then look at the state vector for time 1, we know that that's equal to p times x0. And what we can now do is say, well, but we just said that x0 must be some linear combination of those vectors. We don't know what that linear combination is, but it exists. And then we can bring our p inside and bring our scalars outside, and what you get is this right here. But what do we know? We know that p times v0 is just v0. Why? Because that comes from this eigenpair right here. The eigenvalue is 1. And we know that p times v1 is just lambda 1 times v1. And p times v2 is just lambda 2 times v2. Interesting. What if we keep doing that? So we start here. This is what we get after one step. We just talked through that. For day 2, we have to do p times the state for day 1. But the state for day 1 was given by this linear combination right here. We computed that right here. So we can do again the same trick of bringing p inside and putting it in there everywhere. And then again, it's the case that p times v0 is v0. But this time, p times v1 is lambda, and we already had a lambda, so we end up with a lambda squared. And the same thing here. P times lambda 2 times v2 is lambda 2 squared times v2. So if we look at the limit, as we look at more and more days in the future, that means that we have to look at the limit of this. And if you haven't taken calculus yet, then you don't quite know what the limit means. But think of it as this integer k gets arbitrarily large. Well, think about it. If you take the fraction 1/2 and you keep raising it to a larger and larger power, eventually it goes to 0. It becomes insignificant. So what happens is that eventually these limits here become 0, and you end up with a vector that points in the direction of the eigenvector v0. And bingo, that explains the magic of predicting the weather many days from now. So in summary, it's understanding eigenvalues and eigenvectors that allowed us to explain that when we keep hitting this vector x with p, eventually we end up with a vector that doesn't change anymore, at least not noticeably.